Morgan. I think you're going to find this presentation very interesting. I encourage you to stay through the whole thing. Some of these technologies that he's going to present are phenomenal. And take it away, Matt.
All right, I've started sharing, so I hope everybody can see. Just yell if you can't. So my name is Matt Morgan. I work with the National Radio Astronomy Observatory, and I'm going to talk a little bit about the technology that we use and develop at the NRAO for radio astronomy purposes. I'm guessing this might be a new subject to most of you, so hopefully this will be interesting. And why is it not? There we go. So briefly, I'm gonna start with just a overview of what the NRAO is and what our facilities are. I'm going to talk a bit about astronomical interferometry, which is how we combine data from multiple telescopes to create images of the sky, because I think there might be some interest. I'll talk about some of the components that we develop, the instrumentation that goes into our telescopes, and then I'll conclude with some of our future developments that we're currently working on. So the NRAO, very quickly, we're a federally funded research and development corporation. We build and operate state-of-the-art radio telescopes for the astrophysics community. We're funded by the National Science Foundation, and we're operated by this group called the Associated Universities. That was really started decades ago because radio astronomy, like optical astronomy in the early days, was really an academic university effort. But even the top universities found they could no longer really afford the big facilities that radio astronomy demanded. So they sort of banded together and created this group called Associated Universities to share their resources and build radio telescopes. And that essentially morphed into what's now the National Observatory. So I'm going to go very quickly through the telescope facilities we have. The Jansky Very Large Array is shown here. It's one of the more visibly recognizable ones. You see it in the movies. Contact or Jody Foster, for example. And it's, just to give you some numbers, it's 27 antennas. Each one of them is 25 meters in diameter, and they operate at a frequency range from about 1 gigahertz to 50 gigahertz. This is actually touted as one of the most scientifically productive science instruments in the world in terms of number of papers published as a function of data that was collected with the telescope. Behind Hubble Space Telescope for a while. I'm sure James Webb is catching up if it hasn't already. But nonetheless, still a very productive telescope. It's been around for a very long time. And we just completed a massive upgrade, improving sensitivities, bandwidth, and process data throughput and things like that. A little lesser known is the Very Long Baseline Array, where we have telescopes spread out kind of over the Western Hemisphere. You can see, including as far out as St. Croix and Hawaii in the West. These telescopes are very similar to the VLA antennas. They're 25 meters diameter. There's 10 of them total that operate synchronously, essentially. And they operate from 300 megahertz to 96 gigahertz with a maximum baseline. And very briefly, just a little bit of vocabulary. For us, a baseline is any vector or geographic vector between a pair of antennas in the array, because that essentially determines your resolution on the sky. So your baseline distance versus wavelength tells you what your resolution is. And with this array, we get a maximum baseline of over 8,000 kilometers. In West Virginia, we have the Green Bank, Robert C. Byrd Green Bank Telescope, which is 100 meters diameter. It's the largest fully steerable telescope in the world. For scale, I like to highlight the little pickup truck down here on the ground beside it, just to kind of show you how big this thing is. Like I say, it's 100 meters in diameter, or 2.3 acres, we like to say. Covering a frequency range of 100 megahertz to 116 gigahertz. We're developing a radar capability, and have done some proof of concept studies with this telescope for looking at the moon and other things in orbit, as well as asteroids and space debris and that kind of thing, space situational awareness. So that's an upcoming development. I'm going to talk more about that at the end of the talk. Also, what's interesting about this telescope is it sits in the National Radio Quiet Zone, which is this FCC established zone of sort of radio protection, both for the Green Bank Observatory and the Sugar Grove U.S. Naval Radio Station back in 1958. It's 13,000 square miles, and radio emissions or transmitters in that area are controlled in terms of the radio flux that they can produce. In our case, measured at the focal point at Green Bank Telescope now. You'll notice that there's a couple of fairly large cities in here, Harrisonburg and Stanton, for example, that in Virginia, that are obviously, most people in those cities are totally unaware they're in a quiet zone. Reason for that being that there's a good mountain range, the Appalachian Mountain Range here shields the observatory pretty well. We don't find it necessary to restrict those radio emissions, even though technically it does fall under the jurisdiction. We kind of consider this something of a natural resource, or national resource rather, not natural, but national resource, in that it is, at least in the Green Bank Observatory site, one of the most radio quiet places in the country. However, of course, wireless transmissions are always increasing, what we call radio frequency interference for us. And there's this sort of new proposal out there to create a national radio dynamic zone, where it won't be that emissions have to be zero, but there will be much greater collaboration and coordination between transmitters with the telescopes, as well as other people doing wireless experiments and things like that. So it's envisioned as a kind of sandbox or test bed, if you will, for people to develop wireless technologies in a controlled environment, but nonetheless out in the field where they can really see how things are going to work. And then the last telescope I'm going to mention is currently operating is the please stop. Yeah. What do you got?
Yeah, we had talked about this, and you wanted me to remind you about the availability for people to use these facilities, especially in the quiet zone.
So our telescope facilities are available for anybody to use based on scientific merit of their proposal. So the telescopes themselves are mostly used for astrophysical experiments. And what happens is astronomers will propose for the time, and then they propose to the NSF basically, and the NSF, well, they propose to us, we take it to the NSF, and then time is granted to use the telescopes, and funds are appropriated to us to operate the telescopes and provide the data. But our telescopes do get used for other things as well. In fact, we have a very successful partnership with the U.S. Naval Observatory, for example, collecting geodetic data from the VLBA, which is something I'm going to talk a little bit more about later. So there's definitely opportunity to use these telescopes. They're owned by the government, and so available to anybody who needs them, essentially. I was talking about the Atacama Large Millimeter Array. This is in the high Atacama Desert in northern Chile. It has 66 antennas in the array, with ranging from 7 to 12 meters in diameter. The difference, by the way, the reason we have two different sizes is because when they distribute these arrays, they like to have antennas close together and antennas far apart to cover all the different size scales or resolution scales. But for the closest telescopes, as they point to the horizon, for example, they shadow each other. And so to get them a little more closely packed, they like to have a small number of smaller antennas. With, I think there's 12 7-meter antennas in this array, and the other 50 or so, or 12 meters. That's relatively small by our standards, but the reason is because they operate at a very high frequency, in this case 35 up to 950 gigahertz, almost terahertz operation. So you need really super accurate surface quality down to 25 microns, and to maintain that parabolic shape as a function of gravitational field as you tip, and thermal heating from the sun moving, and wind loading and all that kind of stuff. So these are super accurate antennas for a very high frequency operation. And this is situated at 16,500 feet like I said, in the Andes. Because basically it's high and dry, we're very sensitive to water vapor in the atmosphere at these frequencies. I work at the Central Development Lab, shown here in Charlottesville, Virginia. It's next to a golf course, which makes for a pretty drone picture. But we develop a lot of the technologies for the instruments that go in our telescopes. I'm trying some semiconductor developments in the top two pictures. Actually, thin film on the right, and semiconductor wafer on the left. On the bottom left is some waveguide. It's a waveguide with a mode transducer being subjected to some testing. The bottom right is a rather innovative triple tri-mode orthomode transducer, also that was developed as a sort of a novel concept for polarization isolation on these telescopes. Right. Just to go, please.
Matt. Willis has a question. Go ahead, Willis.
Sure, go ahead.
Yeah, I was just wondering, the antennas in Chile, are they also owned by the government?
So yes and no. So that particular one was actually an international collaboration. So we partnered with Europe and Asia, and it's sort of jointly owned. But we have that is North America has a share of it, and a certain amount of its time is dedicated to North American operations. So yeah, technically that one's shared.
Okay, great. Thank you.
Yeah, international collaboration. The others that I mentioned are entirely U.S. facilities, but that one is international. We have some facilities at the lab that I thought you might be interested in. We have, for example, a very high precision machine shop at the Central Development Lab. This is just a photo I took with my phone the other day of some of our numerical milling machines. We have a really high-end machine in the lower right there, Metzora, which is capable of precisions, they say on a good day, down to half a micron machining accuracy. More typical is sort of 5 micron machining accuracy. Typically, we work with brass, copper, aluminum, and machining to 5 microns typical metrology down to half micron easily. And we're tinkering with 3D printing, but there's a lot of other groups, I think, that do more of that than we do. Upper right also is a computer-controlled lathe, which also is very precise for making corrugated feed horns and things like that, which we use in our telescopes. We also have what we call the Chem Lab, where we do a lot of electroplating, mostly gold, though sometimes with underlayers of zinc, nickel, and copper. Again, there's outside shops that do this, but what we find in our experience is they tend to be more focused on jewelry and ornamentation and stuff like that, and they don't control the chemistry as well as we'd like for electrical properties, which is very important to us, low loss and things like that. So we find it useful to have our own in-house capability. A lot of what we do is gold, either soft gold for wire bonding, which you can see in some of these pieces here, has kind of the more dull finish, and then brightened hard gold, which like these shinier objects, which are good for our contacts or electrical contact surfaces and things like that. And we found ways even to do this inside of waveguides and other tight, subroutine structures, so we can get sort of inner surface conductivities and qualities that we need. We also do a copper electroforming for inside out, what I call inside out shapes, which then is not a unique capability of ours, but something we do, and I'm not sure how many people are familiar, so I just want to briefly talk about what that is. The way this works is we use our very high precision machine shop to make a mandrel out of aluminum. And so in this case, what I'm showing is essentially a aluminum bar with fins precisely machined on it. And we gold plate that to get a layer of gold. Then we grow copper or copper electroform over it, a very thick layer of copper. And then we chemically etch the aluminum out from the inside, leaving that gold surface on the inside of the copper. And finally do a final plating step to make sure the flanges are well covered by gold and whatnot. So what you end up with is sort of the inverse shape. And in this case, it's a corrugated square waveguide, which is part of a phase delay device that we use for converting our linear polarization orthomode transducers into circular polarization. Which is in a very low loss way for us because, again, for radio astronomy, we're looking at very weak signals on the sky, and noise temperature is probably our most important specification. So you can see some real objects, here on the right. There's an aluminum mandrel that was just machined, gold plated, and then it spent a few days in the copper electroforming bath where it got copper deposited on it. And then finally it goes back to the shop where they cut off the ends and etch out the aluminum and make the flanges. And then you end up with these single piece corrugated waveguide devices out here on the right. So that's a very useful capability for us for complex structures. We also use it, for example, for corrugated feed horns, which we use at a wide range of frequencies to illuminate our dishes. All right, so I'm going to talk a little bit about interferometry. Yep, sure.
Real quick, I just wanted to add that people can access
yes,
you for development of these type of
absolutely.
units,
So we engage in direct part sales if it's a part that we already have. If not, if you have a drawing or something, you want some you want to contract for some machining in the shop or electroforming or something like that, we can do that. I actually forgot to mention, and I didn't include these on the slides, we also have very good antenna range capabilities. We have both an indoor and an outdoor range. I think the outdoor range is good down to 100 megahertz or so. The indoor range is like 2 gigahertz up to 100 gigahertz quality, which we use for antenna testing and that kind of thing. And that's also available to outside groups if they'd like to use those to qualify their antennas. So yeah, so all of these facilities are available for use by outside groups that might be interested. Okay, interferometry. So this is the process really of taking data from multiple dishes and combining it to create images. And initially, what that really means is precision timing of the signals, because you're trying to line up wavefronts coherently from all these antennas. And so certainly for the ALMA telescope, for example, where we're operating up to 950 gigahertz, we have to maintain synchronization to within femtoseconds of delay. And this is done on that telescope particularly. This is done with fiber in the ground, where the round trip phase delay in the fiber is actively monitored with test signals going out and back, and then monitored and then corrected with a piezoelectric fiber stretcher or mandrel with a coil of fiber wrapped around it to maintain the overall length of the fiber over a distance of tens of kilometers to an sub-wavelength accuracy at terahertz frequencies. And this also involves then looking at catalog stars in the sky to come up with essentially a phase solution across frequency, which effectively determines the position of those telescopes to sort of sub-millimeter accuracy, which is it's sort of an interesting side product of our process that leads to some interesting geodetic data, which I'm going to talk about a little bit more later. Obviously, for a telescope like ALMA, where the extent is maybe tens of kilometers, we have dedicated fiber. But for the VLBA, where it extends over the whole Western Hemisphere, we can't have dedicated fibers for that. But the very far out antennas, then they each kind of have their own local hydrogen maser, which is a very accurate atomic clock, and that allows the individual telescopes sort of free running to maintain sort of coherency over a short interval. I think it's measured in seconds. I'm not exactly sure what the numbers are, but then the data is recorded and then brought back to a central signal processing facility where it's post-processed to do the image forming. Most of our other telescopes, it's more or less streaming real time. Another question? Thought I heard a beep. Okay.
That was just somebody joining.
Okay. So a little bit how this works. So again, you have a number of telescopes out in the field, and essentially what you have is each pair of telescope, you do a cross correlation of the signals after you've lined them up coherently and got the timing settled. You do a cross correlation calculation on the data streams from that pair of telescopes. Again, that red line, that's a vector. We call that a baseline. And each baseline essentially gives you a complex sample in the two-dimensional Fourier transform of the Fourier plane of the image on the sky. And so you've got a discrete sample now of essentially the frequency space of your image, that is spatial frequencies on your image. And then every pair of telescopes gives you another complex sample. So just take all n squared or impose n minus 1 for 2 pairs of antennas, and you get all these samples in the Fourier plane. And then you take an autocorrelation from each antenna to give you that sort of DC term in the center. And then again, more often we're looking at fairly static images in the sky. So we stare and integrate for long periods of time. And then the rotation of the Earth actually gives you a little more UV coverage or coverage in the Fourier plane as you do that. Once all the data is collected, then we do essentially a big inverse two-dimensional Fourier transform, and you get your image. And we don't see squirrels, but that just happened to be the picture I stole from the web with the proper Fourier transform. But that's just kind of how the process works. What you get, please.
Go ahead. Well, you're muted.
How long does it take to collect the data?
We collect the data, and certain rough data products are available real time. essentially. You can monitor streams of data, and I'll show you later. We build these huge correlators that do the process of streaming data. A lot of it is stored, but it's really too much to store all and process it later. So it's pretty much processed real time. Now, I will say that there's a lot of post calibration that's done in the imaging to sort of deconvolve the beam pattern, the beam pattern and other atmospheric effects and other kinds of things that we calibrate for. So I would say that there's sort of rough data available immediately and more calibrated data, which usually somebody has to sit down with the computer and work on for a few days. We do have sort of automated pipelines doing this, but a lot of astronomers find that they want to have a little more hands-on approach into exactly how the calibrations are done and what sort of corrections they want to take and all that kind of stuff.
Thank you.
That makes sense?
Yeah, it does.
Yeah. So this is a picture of the Very Large Array in New Mexico. One of the things I wanted to point out, by the way, is that you can barely see it in this image, but there's a railroad track kind of running along the arms of the Y here. And these telescopes are movable. These red, I'm pretty sure these red trucks down here in the lower left, they're transporters that can pick up the telescope, move it along the railroad tracks, and deposit it on another concrete pad where there's a fiber optic and power hookup and that kind of thing. So we can reconfigure our array to different spacings and different baseline distances because that gives you your resolution. And they cycle through different configurations about once every year or 18 months, I think. But this matters because when you do this interferometric combination, you get the effective resolution of essentially a dish that had the same diameter as your array. Now, obviously, there's no free lunch there. It doesn't have a sensitivity of such a dish. That's limited more directly by your total collecting area. And again, this, as you can see, this is what we think of as a fairly sparsely filled aperture. Sorry, before I go to that, so like I say, we cycle through different configurations. This is the picture in its most compact configuration where the antennas are as close together as they can get. At its maximum baseline, I think this particular telescope goes to about a 26 kilometer spacing, again, in kind of a Y configuration. I wanted to make the point that radio astronomy is very much a multi-wavelength, multi-messenger business now. This is a false color image of the Crab Nebula, just as an illustration, where each color corresponds to a different wavelength of observations. We have the radio wavelength shown in red, with which was data taken with the Very Large Array in New Mexico. Infrared shown kind of a yellow there, taken from the Spitzer telescope. Optical shown in green from the Hubble Space Telescope. Ultraviolet from the Newton spacecraft, and X-ray data in purple taken by the Chandra spacecraft, all combined to create sort of this one image. And although very pretty, it's also it gives you a lot of extra science that way when you can sort of combine spectral signatures at different wavelengths and redshifts and things like that. So that's just kind of the nature of radio astronomy these days. We combine data from multiple instruments. It's becoming very quickly multi-messenger. That's our sort of cute word for the fact that we don't just look at electromagnetic radiation or light anymore, but now we've kind of entered the era of gravitational wave astronomy with the detection from LIGO of gravitational waves. And it's something we're looking forward ahead to in the future, combining those kinds of measurements as well. So that's what we mean by multi-messenger. I'm going to quickly go through the astronomy stuff because I know that's probably not the first interest of this audience. With the high resolution, though, you can see things you've never seen before. This is a sort of a zoo of protoplanetary disks imaged by the ALMA telescope, where you're seeing forming star systems, these dusty disks of gas and dust orbiting protostars with planets forming and clearing out the material in their orbits and creating these dark rings. And so this is kind of a new observational domain is sort of opened up by the resolution you get from ALMA, which is a very high frequency telescope with a very high, very large array. Therefore, you get this exquisite resolution on the sky. Also, please. Yeah.
How far away is your range for these pictures here?
Oh, that's an excellent question, and I'm not prepared with that answer. I would say that all of these star systems are definitely within our galaxy. I'm pretty sure of that.
Okay.
we do observations all the way out to the cosmic microwave background, which is as far as you can get. But these particular ones, I believe, would be more sort of in our neighborhood of the galaxy. If you'd really like to know, I can get you in contact with the people who would know that, but I don't know off the top of my head. Sorry.
Yeah, that's well enough. Thank you.
Yeah. Also, just a little bit more about the data that we collect. It's hyperspectral. What we call hyperspectral image cubes, meaning you have this image sort of on the left face of this cube here, which might show total intensity or some sort of a spectral feature, molecular line we're interested in. But behind each pixel, literally each pixel behind each one of those is a complete radio spectrum with potentially very high resolution. Again, we're collecting data by staring at an object for minutes or even hours at a time, and you collect just a huge number of samples, and you can take your FFT almost as long as you want if your receiver is stable enough, and we work very hard to make sure that it is, so that you can get spectral resolution down to sub-hertz even if you want. Usually not over the entire bandwidth, but over a limited bandwidth. There's different modes in the back-end signal processing that will give you either more bandwidth at coarser resolution or narrow bandwidth at high resolution. But generally, we're always collecting hyperspectral image data. And this is mostly astronomy, so I'll go quick in the interest of time. Again, you combine data
real quick.
with... Sure.
Real quick, what kind of computing power do you need to for that work you just did on the previous slide?
I'd have to check which telescope this actually came from, but I will skip. Well, I'll get to it soon. We build correlators. We actually build some of the largest application-specific computers in the world to do this. The ALMA correlator, you'll see the picture. It fills a room. I mean, it's rows and rows of racks of computers.
Okay.
So yeah, we build very large computers for doing just that, actually, because we're processing many gigahertz of bandwidth, in real time. This image, this is a Einstein, what we call an Einstein ring. It's a lensed galaxy. So there's a foreground galaxy shown in blue, and you can see even with the Hubble telescope at this time was only capable of this very pixelated image of that foreground galaxy. But with the radio techniques that we use, we can get really exquisite resolution of this galaxy that's lensed by the gravitational field of that foreground galaxy, shown in sort of orange here. And it's the yellow, bright yellow is dust, the dark purple is kind of this carbon monoxide signature. So that kind of shows you how we use sort of nature.
Matt, Eugene, can you explain what an Einstein ring is? I don't know that everybody would be familiar with that.
Yeah, sorry, I was going quick because it's astronomy, not so much technology. But it's the fact that there's this foreground galaxy and then there's this background galaxy behind it, right? So we're here and there's this foreground galaxy and a background galaxy. The massive gravitational field of this foreground galaxy distorts the space-time and causes the light from the background galaxy to bend as it goes around it. And so it's called gravitational lensing. So this ring you're seeing is you get almost a perfect alignment by chance between us and the far galaxies, the two galaxies, so that you get this sort of distorted image of the background galaxy as a ring around the foreground galaxy. And so, yeah, it doesn't, it's not really shaped like that. It's a distorted image, kind of like looking in a curved mirror, but it allows us to get much more signal to noise really on this much more distant galaxy that would otherwise be too far away for us to see clearly. So we're really using the natural gravitational distortion of the foreground galaxy as sort of an extension of our instrument in that case.
And does the color or anything give you some indication of how far behind the foreground galaxy the other galaxy is, the distance between the two galaxies?
Absolutely. So what you're actually seeing here is a processed image where they've done the spectroscopy. They've identified the spectral lines that are associated, in this case, with carbon monoxide, for example. And they've looked at what the redshift of those spectral lines is, and that will tell you what its distance is based on the Hubble expansion scale and all that. So they can absolutely tell how far away something is. They can tell what temperature it's at. They can tell by the broadening, the Doppler and the pressure broadening of the spectral lines, what the velocity flows look like. So you can actually tell quite a bit with the spectroscopy that way. Indeed.
Great, thank you.
Then, Okay, and then there's just want to mention this Event Horizon Telescope, which is really, it's not an individual telescope, it's actually a consortium of a number of telescopes, including ALMA down here in Chile, as well as a number of other telescopes around the world, to combine their data at these sub-millimeter wave frequencies to resolve black hole images. You all have probably seen in the upper right there, this image which was taken a few years ago. Of the black hole at the center of the M87 galaxy. And that just kind of shows you what we can do with the resolution. People tend to look at this picture and they say, oh, why is it so blurry? And my response to them is always that this is actually the sharpest image you've ever seen. And you really are only seeing a couple pixels worth of data here, but it's been processed and enhanced with the resolution of basically a whole hemisphere's worth of telescopes, sub-millimeter wave frequencies allows you to see this. The reason I bring this up also, I want to point out that image processing is very much an active science, active area of science. How do you get the most image fidelity out of the least amount of data? And that particular data has been processed and reprocessed. And there was a paper published. This is actually not from NRAO, but from another group. But we do this kind of work as well, figuring out better ways to sort of estimate accurate images from what essentially amounts to a sparsely sampled Fourier plane. If you remember, I talked about how the interferometry works. And they're able to get much better resolved images, for example, of the event horizon, this black hole that way. So we actually have a very active and very capable sort of image processing algorithm development department as well. And geodesy, I want to talk about real briefly. So again, remember that in order to do the synchronization for the interferometry, we end up determining the positions of our telescopes to a fraction of a wavelength. And with that, we can actually monitor some interesting things, including, for example, the so-called Earth orientation parameters, where we're monitoring, for example, the fact that the Earth's rotation rate, 24 hours per cycle, in fact, fluctuates at a very small amount every day as a result, I believe, of tectonic plate shifts and the fact then that essentially the rotational inertia of the Earth is changing on a very micro scale. And so the daily period changes every day by a small amount. And you can monitor that by tracking the stars and determining the positions of your telescopes on the ground. You can also monitor tectonic plate movements, for example, over many years. Again, if we know the positions of these telescopes to a fraction of a millimeter, and they've changed by a few millimeters, and consistently over the years, you see them changing their position over millimeters. You can do geologic studies that way. And this celestial and terrestrial reference frame business is a very great importance to people doing global positioning services and stuff like that as well. So that's sort of a side product of our telescopes. And that data is available. I have a contact listed in the end of my talk here who can certainly plug you into that kind of information if you're interested. And I'm going to talk a little bit about components and instrumentation. Probably the most immediately recognizable for us is the cryogenic low noise amplifiers that we developed. So again, noise is sort of king for us. And so we want to have the lowest noise receivers we can. And so we use cryogenically cooled amplifiers. Typically these days, they're indium phosphide high electron mobility transistors cooled to a temperature of about 15 Kelvin. We actually do have the capability of cooling more than that, and we do for some of our other components I'll talk about later. But what we find is that the transistors themselves really don't improve much below that much. So that's the temperature we target. And with these, we get noise temperatures equivalent to about 5 times the quantum limit for a coherent detector, which translates loosely into sort of a 5-photon detection threshold. That works over a range of frequencies from sort of a low single-digit gigahertz up to 100 gigahertz or so. At its minimum point, it translates to a noise figure of about 0.04 dB, for those who don't really think in terms of noise temperature as we do. I would be remiss in not admitting that there are actually lower noise amplifiers out there. The quantum computing industry is really pushing the envelope in that area. We were fairly excited about that actually at first, thinking that, well, finally, there'd be this sort of commercially driven industry with developing some technology that we could use. Unfortunately, we quickly learned that their amplifiers are so low power that they would literally saturate as soon as we pointed at the cosmic microwave background, which pretty much makes them useful to us. So The positive spin on that is we don't get noise temperatures quite down to the quantum limit, but we do get a lot better dynamic range with these kinds of amplifiers than those you'll see in quantum computers. Once you get above 100 gigahertz, the transistors start to sort of lose their gain bandwidth product, and so we need to go to a different technology. And the device of choice is the superconducting mixer, or SIS, tunnel junction mixer. That's essentially a parallel plate device with a niobium, superconducting niobium on each plate, and then a dielectric most of the time these days on aluminum and aluminum nitride, although we are experimenting with other recipes. But what you get there is essentially a tunnel junction. It looks kind of like a capacitor, but when you get you reach a certain threshold voltage, the carriers will tunnel through the dielectric and jump from one plate to the next. And it's a very sharp corner turn on of the current. Much sharper than room temperature diodes. In fact, I think it's been called the sharpest nonlinearity in nature. And so that gives us very efficient mixers with near quantum limited performance between about 100 gigahertz and a terahertz. And so the ALMA telescope down in Chile, for example, uses a lot of these kinds of devices. And we also do custom MMIC development when needed. I deal with this a lot myself, and we do use commercially available chips whenever they're available. I find that commercial offerings up to about 50 gigahertz or so are very sufficient for me. I can buy whatever I need. Above 50 gigahertz, when I was in grad school, there really just wasn't much available commercially. There's a lot more available now in commercial product catalogs, but they tend to be narrow band above 50 gigahertz or so. You might have a W band amplifier with 5 gigahertz of bandwidth at 100, for example, or 90, something like that. But for radio astronomy, the scientists want to collect DC to daylight. Really, they'd like to get as much as they can. So we want to cover at least waveguide bandwidth with all of our receivers, and that means that we end up doing custom chip developments of various kinds. This is a W band power amplifier in the upper right. We do partner, by the way, with commercial fabs. We don't have our own semiconductor fab. We just have the design capability in-house. And you can see the device in the upper right was fabricated by partner BAE Systems, short gate length gallium arsenide process. And in the lower right is a Schottky diode broadband mixer developed by us, but fabricated at United Monolithic Semiconductor in France. And then we put these together into integrated analog, digital, and fiber optic receiver assemblies. And I just showed sort of an exploded view of one here on the right. This really goes from the centimeter to the millimeter wave range. These encapsulate typically all the conversions, basically the entire signal path for us after the cryogenic amplification. So we go to the warm side and do the RF to baseband, analog to digital, and copper to fiber conversion in one module to send it out away from the focal plane of the telescope to a signal processing facility that might be tens of kilometers away. We also do a lot of in-house sort of test sources for the higher frequency stuff where such things are not as easy to buy. And then finally, at the larger scale, we do full receiver assemblies. This is done at the Central Development Lab in Charlottesville. And just to show you, on the left is the ALMA Band 6 cartridge, which covers a 211 to 275 gigahertz. This is the warm and cold cartridge assemblies. This kind of gives you a visual of the fact that, again, we're cryogenically cooling these things. For these, it's a superconducting mixer. Those have to be cooled to 4 Kelvin. So we have a 3-stage refrigerator, which basically means you have a fridge inside a fridge inside a fridge. And you can kind of see that in the stack here. And this cartridge sort of plugs into a hole from the bottom. And the base plate here is really the vacuum seal. This first sort of gold disc is the 77 Kelvin is attached to the 77 Kelvin stage. There's a 20 Kelvin stage, and then there's a 4 Kelvin stage. So most of the sort of high frequency electronics is all up here in the top, cooled to a temperature of 4 Kelvin. We do, in fact, have a millikelvin refrigerator in the lab, the CDL, for some device research that we're currently doing, with an ultimate temperature, I believe, of 7 millikelvin for some very exotic sort of superconducting devices. And then here on the right is the, please.
Yeah, I'm just going to ask a question. Does low gravity provide any value from a production perspective, or?
low gravity. So you talk about space-based applications, probably?
Yes, yes.
Yes, so that's an interesting question. So we don't, our mission and our charter really is ground-based radio astronomy. NASA's territory is really the space-based stuff. So we try not to step on their toes too much, although we do end up collaborating quite often with NASA and other groups doing spacecraft. We'll build instrumentations like we participated in the WMAP project, which was a spacecraft many years ago, where doing cosmic microwave background studies, and we built all the cryogenic amplifiers for that, for example. I don't believe the low gravity had any effect on anything we were doing. Of course, the fact that it had to be space qualified was a little bit of a difference for us. We don't normally have to do space qualified electronics. And that, as I'm sure many of you know, leads to a whole lot of qualification, quality control, and testing and whatnot. Like I say, I'm not aware of anything that we do that would really be affected by whether it's gravitational or not, other than like these receivers, for example. Again, this is this particular one's a several hundred gigahertz. We did terahertz, almost terahertz receivers for this. And there was a lot of concern about, as the telescope tips, for example, we did a lot of finite element analysis of the mechanics of how this would flex and offset the pointing and affect the focus of it and all that kind of stuff. Of course, that all gets easier when you're in zero gravity, but you got to worry about the vibration of launches and stuff like that. Also, the cryogenics, we tend to do closed cycle helium refrigerators. And I know some of those refrigerators are sensitive, depending on what style you have, are sensitive to tipping in a gravitational field. They kind of want to be upright, which is just a limitation of that technology. So if we're developing something for space, we would take that into account. But otherwise, it doesn't really affect us all that much.
Okay, thank you.
The correlator. So I was talking about this earlier. This is a picture of the ALMA correlator. Actually, this is 1/4 of the ALMA correlator because it's 4 rows of racks just like this, and you're standing in one of those rows here, and you can see the computer cards plugged into that. And also, I just want to point out, I don't know if you can see in this picture here, here's a technician replacing one of those circuit boards, and he's wearing an oxygen tank because this particular computer exists at the ALMA site at 16,500 feet. And although mountaineers might be used to that, our electronics technicians aren't so much. And so a lot of people who work on these kinds of things at the site end up having to wear oxygen masks just so they can work more comfortably. But like I said, this takes the data from all the telescopes, and you're talking from ALMA, I think you're talking about 16 gigahertz instantaneous bandwidth from 66 antennas, cross-correlating every pair of those, so n squared times 66 antennas, and doing big FFTs, all in real time, essentially, to produce these hyperspectral image cubes. Just the cool numbers, it consists of 134 million processors performing essentially 7 petaops. That said, it's actually a fairly basic computer. All it does is multiply and add all day. So it's kind of programmed and optimized to do exactly what it does and not much more. I'm going to shift gears and just talk a little bit about commercial partnerships. We do occasionally develop technologies that have been found to be useful to other industries, and we hope to continue to do that, which is one reason I'm here today. And just I have to brag on one of our successes there. Many years ago, I was working on receivers, and I was trying to resolve some issues with stability that had to do with out-of-band interactions between broadband, mixers and amplifiers and the filters. Conventional electronic filters, for those who know, reject stop-band signals essentially by optimally poor impedance match, but by reflection. And realized that I could get a much more stable signal path if I could terminate unwanted signals in a nice 15 ohm resistance as opposed to reflected. And we came up with these topologies that do that, both lumped element and transmission lines. And it's really satisfying to plug this into a simulator. If you use ideal components, you just get a little perfect dot right in the center of the Smith chart from DC to infinity. And you can realize even all the optimal, traditionally optimal filter responses like Chebyshev and Butterworth and Legendre, whatever you might want, but with no reflection of any frequency. And these were then developed into passive dye. This is a little gallium arsenide dye that were created one of those filters on it. And it's, it's just built up in this case of spiral inductors, MIM caps, and thin film resistors on a substrate, which then could be packaged into a surface mount package like you see here, if you're going to use it on a circuit board. And this has been one of our big commercial successes. We partnered with Mini Circuits, who I'm sure many of you are aware of. And these are some ads that they've put out in industry journals to kind of sell these. And I'm particularly fond of the one on the right because it kind of shows the origin of this as a radio astronomy technology, but that found use in a lot of other applications as well. So hoping to do more of that here. Let's see, how am I doing on time? I hope I'm all right. I'm going to talk a little bit about what we're looking ahead to. We're in the process of developing and proposing to the government the new telescope facility called the Next Generation Very Large Array. This is a artist conception, but it'll consist of 263 antennas in the current conception anyway, with diameters ranging from 6 to 18 meters, operating from 1 to 116 gigahertz, and having a almost 9,000 kilometer baseline. So you can kind of think of this as filling in the intermediate spacings between the VLA, which currently sits in New Mexico with a 26 kilometer baseline, and the VLBA, which is again this sort of hemispherical size antenna or array. And we want to fill in the intermediate spacings there to get sort of good image quality over all of those resolution scales. And so this is sort of a preliminary map of where the telescopes would go. There's a central core where they're fairly densely populated, and then you get these spiral arms coming out into the neighboring states, Arizona and Texas, a little bit down in Mexico, and then the very long baseline antenna is shown in purple here, including in Hawaii and over here in San Croix. And so this is a telescope facility that's under development now. Oops. I'm sorry. I'm going to show my video. There we go. Sorry. This just gives you another view of that. This was, again, an artist's conception. It was actually an older antenna design. You might notice it's shaped a little different now. But again, this is 18-meter dishes, hydroformed, I believe, for sort of large-scale manufacturing, but precise dish, low-cost dish. And we're going to zoom out here in a second. And while we're doing that, I'll point out, so this is conceived as an international partnership, but with more than a 50% share in the U.S. To kind of maintain control of it here. They're partnering with some other groups to help fund it. And all right, so here you see that was a central core, fairly densely populated, replaced with a symbol now, and then little icons for some more spread out, far out antennas. And as we continue to zoom out, this is New Mexico. As we zoom out, you see the border with Arizona and Texas start to show up, and telescopes as we get further and further away, and out to the point here where you're going to start seeing the little pink dots showing up with the long baseline antennas over, again, sort of the Western Hemisphere. And they're a little hard to see, but there's a pink dot way over here in Hawaii and a pink dot over here in San Croix. So I mentioned at the very beginning that we're developing a radar capability with the Green Bank telescope in West Virginia. We did some preliminary experiments with a 700-watt transmitter on the GBT. The reflection, in this case from the moon, was received by the VLBA, which is a very long baseline array. And we were able to capture this image of the Apollo 15 landing site. This is a radar image with a 1.25 meter resolution, which they're telling us is the highest resolution images ever taken of the moon from the ground, but from the Earth's ground it is. Obviously, an astronaut standing on the surface with a camera would do better, but from the ground, these are the finest resolution images ever taken. And this is another example from that test campaign of the Tycho crater, showing in this case at 9 meter resolution. I think it was actually 5 on image, but we were looking at it a little bit around the curve of the moon, so there was a projection effect which made it 9 effectively around. We have an upgrade plan for this to do 500 kilowatts. So again, this was a 700-watt transmitter. We're going to upgrade that to 500 kilowatt transmitter on the GBT, with envisioned use for planetary defense, space situational awareness, as well as geoplanetary science, looking at things like asteroids, comets, planets and moons and stuff like that. This was kind of a capability that Arecibo used to have before it was destroyed, very unfortunately, by a hurricane. And so there's kind of this void in radio astronomy that we're hoping to fill with this and have a big upgrade at the same time. I believe my last slide here, I have an image of this just to point out that by receiving with an interferometric array, we get full phase information, full phase coherency. And with that, we can get full three-dimensional sort of topographic radar images, again, at very high resolution. You can see that, again, from this image of the central mountainous peaks in the center of the Tycho crater. You'll notice an image credit to Raytheon because we've partnered with them. You know, we're not traditionally transmitter people. We've been passive receivers for most of our existence in radio astronomy. And so we're partnering with them to develop the transmitter, and also a lot of the radar processing algorithms comes from them. So they've been our partner on that development. Oh, sorry, I guess I do have a couple more slides. Also collaborating with Harvard-Smithsonian Center for Astrophysics on this proposed spacecraft called the Black Hole Explorer. Again, if you might remember me talking about the EHT, where we combine radio telescope data from all these telescopes around the world. They want to add a spacecraft to link up with these telescopes to give us an extra set of baselines, an extra N baselines with higher resolution. And so this black hole image, this was a simulation of it, which we could get with the ground-based telescopes. We'll get a much finer resolution. Not only at the event horizon, but the photon ring of the black hole, which is, again, of scientific interest. And additionally, with the resolution and sensitivity that we had with the EHT on the ground, there were really only two black holes that we could actually see, I believe, because there's the one in the center of the Milky Way galaxy, which we've imaged, which is relatively close to us, and so therefore appears relatively big from our perspective. And then the one in M87 we could see because it happens to be one of the largest black holes known, even though it's in another galaxy. It's so huge that again, it's big enough for us to see. But with this extra baseline, this extra telescope out in space, we'd have sufficient resolution to see hundreds of more black holes, which would definitely improve the science that we can do that. I think this is just what I said. And then lastly, Eugene asked me to include a couple of things. Contacts at NRAO. I've included a sort of a set of people you might talk to. You can always reach out to me and I can refer you to the right person. If you have any kind of question about how we do the astronomical imaging or the interferometry, we have an Ask an Astronomer page with a astronomer assigned to it 24/7. The central development lab, where we have the machine shop, the chem lab, and a lot of the component development and any kind of component sales you might be interested in would go through the CDL. I'm going to refer you to my boss, Assistant Director Bert Hawkins. He'd be a good entry point as well. If you have a question about a specific technology, cryogenic amplifiers, superconducting mixers, or whatever, he could refer you to the right person. We have a tech transfer officer, Jeff Pixton, who deals with licensing, for example, like the reflectionless filters. If you want to license one of our technologies for commercial use, he can help you with that. Eugene mentioned that there might be some interest in the geodesy data from the VLBA, and Dr. Walter Burskin would be a good contact there. We also have student programs, which I'll talk about in a second. We're very interested in getting students for internships and co-ops, and Jim Bratt's the coordinator for that. And again, if you're interested in, the SIS mixers, those are fabricated at the UVA Microfabrication Lab here in Virginia by a group headed by Arthur Lichtenberger. I believe, in fact, they're the only lab in the country now that makes these specific superconducting devices, the SIS mixers. There used to be a couple of these, but they kind of got out of the business. So it's kind of a one-stop shop. And then lastly, our needs and wants. We're always looking for partners who have advanced fabrication capabilities. For us, it's very much about performance, and specs, broadband sensitivity, low loss, that kind of thing. So people who have advanced semiconductor, thin, thick film, or other device fabrication capabilities, we'd love to talk to you, see what we can make with you. Looking for collaborators on tech developments of mutual interest, and of course, always interested in students for internships and co-op programs, both in astronomy and engineering. I would tell you that if you look into that, we have a very healthy and mature pipeline of students in astronomy, and we're trying to grow it more in engineering now. So there's a lot of interest in getting engineering students in there. And then what we can offer in return, like I say, we have precision machining, metal plating, electroforming capabilities, as well as antenna range measurements, which I neglected to include in these slides. We can do direct component sales of parts that we have, like our cryo-LNAs, for example. We can set you up with, or Walter can set you up with some of the geodetic data that we produce as sort of a side effect of our work. And again, with the coming radar capability on Green Bank, I think we have a lot to offer for people who might be looking at tracking orbital objects and debris and whatever else. So radar capability from the, very powerful radar capability from the ground is also something that we can offer. So I think that's my last slide. I'll leave my slides up in case any questions. People want to direct me to a previous slide, but with that, I'll open the floor for questions. And then
yeah, I guess one question, the space situational awareness, what is the timeline for those again?
Excellent question. I'm not a direct participant on that program. I think you're talking about a few years before the full capability is reached. I mean, we have, again, sort of the little test, say the little 700-watt test transceiver on it now, but the upgrade, I think, is going to take a couple of years before it's ready for user.
Okay. All right, thank you.
Mm-hmm. And then
Major Best, are you able to unmute? Okay, so I don't know if you can unmute. So the Major Best asked if did I understand you design mimics? Any consideration about remote power strategies?
We do design mimics as needed. I work on it. A couple other people at the lab have access to that. Remote power. I assume you mean like wireless power transmission or something like that.
Yeah,
if that's what he means, I have not heard of any work that we're doing in that area. Our telescopes tend to be wired in pretty good, and I would say, in fact, that we'd be a little wary of it as a technology, even because we're very sensitive to interference, both outside and self-interference as well.
to support power beaming, wireless power transfer beaming, or space-based solar power.
We haven't done any work in that area. Like I say, even the radar transmitter is a bit of a departure for us. So we're partnering with outside groups who have more experience in that kind of thing. Yeah, so I'm afraid that it's not something we've done.
Would that be a conversation that you would be interested in having?
Sure. I mean, we'd always love to hear what's available. We'd have to think about how it would sort of plug in and benefit our systems. But yes, I could.
Yeah, or actually their usage of your components.
Sure, absolutely. We'd love to see our components used. Yeah, absolutely. Anything these can be used for, we're happy to support that. Yeah,
because anything you could do at a higher frequency, I mean,
yeah,
you're actually going to get a much finer beam. You're going to be able to do a much smaller collection array at the receive site. So yeah. So I'll put you guys together. Sunil, Mr. Dixit.
Yes. Hi. Good morning, Jane, and good morning, Matt. So what sort of collaboration are you looking for on the semiconductor devices?
I would say that it's again, as you can tell, radio astronomy is very multidisciplinary, and we have all kinds of electronics, from the receiver electronics, cryogenic room temperature, digital computing, local oscillators, timing reference distribution, all that kind of stuff. So the door is very wide open to all kinds of semiconductors. I would say that our need tends to be more in terms of what's not already available. High frequency broadband circuits. So just a case in point, for example, for the NGVLA telescope, I have to do a W band receiver that covers 70 to 116 gigahertz. with 30 dB of gain and enough headroom to be, very, very, very linear, with the integrated noise over that band. And that's a very tough spec actually to meet. And I looked and I looked and I looked and couldn't find a part. And then I tried to say, well, okay, can I design a part? I couldn't even find a fab process that was up to it, that was commercially available. I eventually then did come across a company, Teledyne, which has a very excellent indium phosphide HBT process. And they were making amplifiers that did meet our specs and those frequency ranges. And so that was kind of a godsend for us, but it's not really open as a boutique fab, right, for me to come in with my own designs. So, 3-5 semiconductors, whether it's gallium arsenide, indium phosphide, gallium nitride, IMPs, HBTs, we'd like to see what you have, what you can do, and we'll see if we can, use it in any part of our system. Similarly, if anybody out there does any kind of cryogenic work, we'd like to talk to you because, we do some of our own qualification characterization of transistors at cryogenic temperatures. Data is not readily available. So we usually have to test ourselves. And what we find is that a lot of people who do fab appropriate devices don't test them cold and don't control the process such that the cryogenic performance is even repeatable. So that would be of interest to us. Of course, we're also interested in low power, high speed digital electronics and all that kind of stuff. I'm sorry, I tend to ramble on, but bottom line is it's a very wide field. Wide answer.
Yeah. Were you looking at anything on FPGAs?
Absolutely. We have people who do, involved in building the big correlators, and there's a lot of debate over whether that's better done with ASICs or FPGAs. I think a lot of people are leaning towards FPGAs these days, and we certainly do a lot of FPGA development. It's not my particular area, but I can put you in contact with the people who do, and they would be very interested in talking to you about what you have. And then
absolutely, thank you. I'd appreciate that.
Absolutely, yeah. And then GPUs is another area of interest, by the way, along similar lines.
Well, and then what about quantum? Because I know Dr. Dixit and others. I don't know if you work with Southern Methodist and the Darwin Deason Institute of Cyber and Quantum.
I have not worked with them directly. We're very interested in quantum and seeing, first of all, where our technologies can be used and what they have that might be useful for us. Like I said, there was, radio astronomy for much of our history. We've kind of felt like, we're a small fish, in the semiconductor and electronics industry, and so we can't really drive industry in the direction we want it to go. And so we were really excited, when quantum computing kind of came a bit, into its own, thinking that, well, here's another cryogenic, electronics application that will have a lot of common ground with. And we were a little disappointed the LNAs kind of very quickly went in different directions. But we're still keeping our eye on it and thinking that there's going to be a lot more, cross utility there than we've seen so far. So I can't point to any heavy ongoing collaborations, but I think it's something we're keeping an eye on and definitely interested in doing. And then
right. I mean, the cryogenic temperatures really go down to millimeter kelvins. So millikelvins, rather. I'm sorry. And so I don't know if that's something you guys are interested in.
Yeah, I was telling you, we do have a millikelvin doer. We're actually looking at that for an amplifier device called a traveling wave kinetic inductance parametric amplifier, or TKIP, which uses the kinetic inductance property of superconducting film with a local oscillator pump to create a parametric amplification effect. We think these have the potential to give us very low noise gain at very high frequencies, but it's still a technology very much under development. I don't know if such a thing is of interest to quantum computing. We could certainly collaborate on that.
Well, it's part of it. I mean, it's all depending on the frequencies you're looking for also.
Yeah. I actually have I was going to say I have a project right now. We're becoming concerned with interference from communication satellite constellations like Starlink and others coming along. And I've been working with Starlink. They've been very, very good to work with, actually, in helping us find ways to mitigate that interference in our telescopes. But nonetheless, we're actually looking at developing, for example, superconducting notch filters to notch out specific frequencies where they transmit that would that sort of overload our receivers. And so there we're looking at higher temperature superconductors like YBCO, for example. Whereas most traditionally for radio astronomy, we've been interested in the superconducting devices, which are sort of 4 Kelvin and below, and we use elemental superconductors like NRAO. So we're looking for industry partners to kind of help us with sort of a high temperature superconductor, thin film circuitry.
Right. So most of the frequencies are between 100 megahertz to maybe about 50, 60 gigahertz. They really don't go into the 300 gigahertz range.
No, but of course we do a lot of radio astronomy down at centimeter waves too. So.
Okay. All right.
And then we go all the way down to the.
But that'd be a specialized. That would be a specialized circuit that you'd have to build.
Yeah, of course. So there again, we're just kind of looking for fabs. Who has the fab capability to do thin film YBCO, for example. And then
Hey.
Thank you.
So Matt, you said that your volume really isn't, or you're just a small entity, but I worked in radar, and I worked everywhere from HF into well into millimeter wave, and that whole millimeter wave wireless power transfer where you're looking between either at microwave or laser and trying to balance that out. I would think that there are enough people out there that you could drive some of that development if we just get those people together.
I agree. Yeah, if we just find the common interests, then certainly we can do that. About our quantities, by the way. I'm sorry. There we go.
No, go ahead. I'm sorry. I was just asking if there are any other questions.
I was just gonna say in terms of our quantities. So yeah, we on the low end, I mean, like VEX, this spacecraft we're collaborating with CFA on, for example, that'd be one receiver. So a couple of prototypes, a couple of polarizations, but then basically one handful of receivers. Whereas in something like the NGVLA, where we've got 260 antennas and there's 6 bands and 20 receiver modules for each band and dual polarization, all that, you end up very quickly building, many thousands of some of the components. But that's kind of the scale we get at. We don't really ever get into building millions of anything.
And you're always going to be focused on a very broad band. I mean, you're never going to give up the lower frequency bands for the higher.
Yeah, we tend not to. And then telescopes, we and that's the difference between us again, I think, and some of the university groups that do radio astronomy, for example. They do more application specific instruments where we're going to build this radio instrument to do a specific, observation of a specific target in the sky. Whereas what we build as a national observatory, we tend to build sort of general purpose instruments that has to cover a lot of scientific ground. And so we tend to cover a lot of bandwidth with all of our antennas. And just for economic reasons, our individual receiver channels, we want to cover as wide a bandwidth instantaneously as we can. And so, like I say, at lower frequencies, it tends to be 2 to 1, 3 to 1, bandwidths, instantaneous processed bandwidth. There's technologies for doing 10 to 1, but we can't afford to give up our sensitivity and performance either. So that's kind of the compromise. At higher frequencies, it tends to be more sort of octave bandwidths because of what you're limited to by the waveguides and stuff like that. And then life.
Thank you for that. Any other questions? Jeremy, go ahead.
Yeah, sorry, I was really late coming back and had to miss part of your presentation, but I quickly read the comments back and forth. Are you familiar with a company called One Radio?
I'm not.
Okay, so I got to see some of their stuff a while back. They're focused primarily in the communications frequencies, but they have a really neat technology, if I remember correctly, that's able to be broad spectrum, to watch a lot of different frequency concurrently at high frequency, high resolution. And I don't know, you may already rapidly exceed their capacities or not, but it's just a technology I'm aware of that you might be worth looking into.
I'll take a look. Thank you for the reference. Absolutely. Yeah.
Can you
Never
put
know what
something
you're
in the
gonna
chat,
discover.
Jeremy?
Sure. I do not currently have a contact with One Radio personally. It's been probably 5-10 years since I worked with them.
Okay.
I assume I can Google One Radio probably and
Yep.
find it.
Yep.
If it's okay. I'll definitely check them out. Thanks.
All right. Anyone else?
Ended life.
Well, thank you, Matt.
So
My pleasure.
I have a
oh,
comment.
wait. Yeah, go ahead,
Please.
Brian.
Matthew, I'd just like to mention DARPA's Xena program. They're trying to figure out how to amplify some of their images by 10 or 20 times. A lot of the things I think you're skilled at might benefit that program.
Okay. I'd love to talk to them. Absolutely. Thank you.
Do you have a contact there, Brian? In that?
Yeah,
Life?
I could send him an email.
All right, that'd be good. I appreciate that.
Please do. Thank you. Ended life.
Anyone else? All right. Well, thank you again, Matt. I think it was great, and
Your
I
pleasure.
look forward to having the other presentation, working that out, where we can talk about the data that's actually collected and how it's available. I know one thing that we had talked about in the past, but you do have a lot of data that goes back many years that can also be accessed, and actually some of that has been accessed recently, when new things are discovered or places of interest are identified and people want to see what's going on.
Absolutely. I should have mentioned that. You're right. We do keep a data archive, and a lot of astronomers publish new scientific results just by combing the archive and seeing what they can find. So that's available to people can use it as well. Ended life.
All right. Well, thank you again. Before we go, anybody have anything for me from the earlier presentation?
Ended
Any
life.
other questions, thoughts, comments?
Ended life.
Could you put up his slideshow, the contact slideshow, just one more
Oh, yeah,
time?
put up your contact slide.
Absolutely. Let me just do that real quick. Ended life. That one? Ended life.
That's it.
And you'll have my slides that you can post, right? Ended
Yeah.
life.
Yeah, your slides will get posted. And if anybody wants a copy, they can always reach out to me through email. I think I could turn it into a PDF and email it, but otherwise it would need to be
Ended life.
through some sort of a document transfer, because I think it's too large to email as a PDF, or not as a PDF, as a PPT.
Yeah.
Okay, so if you wouldn't mind, Matt, just leaving this up, I'm going to go
Sure.
ahead and call an end to the meeting. We'll leave the slide up for another 2 minutes, I guess. So if anybody wants to take down any of the information, they can do that. But other than that, thank you everybody for being here. Great questions, great interaction. Thank you for the comments. I think there's some possibilities here. I was really interested in what really drew my interest to NRAO and to Matt was actually the work that he's doing and the electronics development side of it, and also in access to their data.
Thank you for the opportunity.